There's a derivation in your book that I did not do in class where we show that the change in enthalpy is equal to the heat at constant pressure. All right, and certainly if you were a chemical engineer, you might do reactions at various pressures. Okay, the Haber process is a process that takes hydrogen gas and combines it with nitrogen, and it makes ammonia. Let's see, what do I have to do here? 3, 2, not 2. Did I balance it correctly? There we go. Okay. So it takes this process. Essentially, we have nitrogen in the air. We talked briefly about this earlier in the class. Nitrogen has how many bonds? Anybody remember when we were with dot structures? Triple bond between those nitrogens. So it's really held together tightly. And so it's hard to break up this nitrogen and make it into a form that can be used by, well, essentially plants. Okay? Used by plants. So plants can't do this on their own. All right, naturally what happens is some plants actually have a symbiotic relationship with bacteria. So you may have heard that beans, legumes, we'll go with legumes for the greater category here. Legumes can actually fix their own nitrogen, but they don't fix it. They provide little homes in their roots for bacteria that will do this fixation for them. Okay, so they take this nitrogen, which is inaccessible to plants, and they turn it into ammonia, which is accessible to plants. Okay, so we don't rely completely on plants to do that. In fact, we rely mostly not on plants to do that. In terms of making fertilizers, we have the Haber process. Okay, but the Haber process here, which involves taking a lot of heat and a lot of pressure, and you use that to make ammonia. So let's talk about heat. Let's put heat over here because we're going to talk about that today as well, right? Heat as a reactant. Heat can be a reactant or product. If heat's a reactant, is this exothermic or endothermic, by the way? We've got those terms, exothermic and endothermic. Endothermic, right? I have to put in heat to make that reaction happen. I don't get heat out. But this is why we can have so many people on the planet today, because we can actually fix nitrogen to make fertilizer to be able to fertilize fields so that we can actually grow enough plants to actually keep everybody alive. Okay. I'm currently listening to a podcast, The Fall of Civilizations, and I'm only a little ways in, but only a few episodes in. But you keep hearing that this civilization or that civilization fell because they wrecked all their cropland, or they overused their cropland, depleted all the nutrients. There were too many people, and then it's gone. It's a cool podcast if you're interested in listening to it. If you're an Elon Musk fan, who I'm not, it's like his favorite podcast. Okay, so we've got heat of solution is what we're talking about here, though. I guess that was a bit of a tangent, but an important one. This is an important thing. But the point here was that we just kind of dump solutions together, right, at air pressure. And so at constant pressure, the pressure doesn't change over our reactions, and so we don't need to worry about, when we talk about heat, that's the same as change in enthalpy. If the pressure was changing, then it would be more complicated, but not for us. So heat of solution is the amount of heat absorbed or released when something dissolves. So I've given you examples before on this. Another example would be, you know, if you make up a basic solution, you make up a solution of sodium hydroxide. So let's take, if I take sodium hydroxide solid, and I go ahead and I dissolve it in water to make sodium hydroxide aqueous. Okay, sodium hydroxide is a base. It's really corrosive. You got to be super careful around it, but it comes in these pellets. If you throw those in water, that solution gets really hot, so we get heat released when you do that. Okay, and I guess, you know, I've talked about chemical cold packs, but I think if I remember from like some days of skiing, there used to be chemical hot packs too that you like could put in your gloves. You'd have like a glove and you'd have a packet. You'd break something and you'd put the glove in the packet in the glove, and it would make your hands warm for a little while. So probably not sodium hydroxide, but maybe I would just be worried if that packet broke and it was sodium hydroxide. So we've got this heat that's produced, and so we can quantify that using calorimetry. All right, and generally we're chemists, so we're concerned with things per mole. All right, you may not have noticed this yet. We're going to start talking about heats of reaction, and we're going to be, we've talked about them maybe in grams so far, but really chemists care about how much of this happens per mole is kind of the general units. And so we're going to say that heats of solution are generally reported per mole in calories or joules per mole. And so we want to be able to do that sort of thing. So let's go ahead. And what's an important equation for us in terms of this is we're going to have a calorimeter where we're going to be measuring things. We're either going to have a calorimeter where we're measuring things where we have, this is a heat capacity of an object, right? This coffee, this could be a coffee cup calorimeter. It'd be pretty bad because it's not well insulated. But other than that, it wouldn't be a bad deal. So this has a heat capacity. There's a certain amount of heat I would need to put in this to raise the temperature of it 1 degree. Okay, that would be what the heat capacity would be, 1 degree Celsius or Kelvin. Or we might have a problem where we just kind of neglect the object, and all we care about, we say, hey, we've got an insulated object, and all we care about is the water inside. So we just say, hey, just the water, and it's insulated well enough, we don't need to worry about anything else. And so in that case, we would use the specific heat capacity times the mass times the change in temperature. This would be the specific heat capacity of water. Right, and that's going to be per gram. And I'm just going to say down here for water, because this is a more general equation over here. It's going to be 1 calorie per gram degree Celsius. So in other words, it takes 1 calorie to raise the temperature of 1 gram of water 1 degree Celsius. Okay. It's all kind of review, hopefully. Mostly review, let's say. Okay. Let's go on to a problem then. So we're going to need one of these equations. I can't remember. Okay, I couldn't remember what problem I pasted in here. What did I do? I must have grabbed this one off the internet because it's not in your book. I couldn't find one I liked. Or actually, I know it was the problem. There was only one problem in your book of the even problems that was one I liked. So we'll do this one instead. And we've already done it last lecture. So in a chemistry experiment to investigate the properties of a fertilizer, urea. Okay, I'm going to subject you to some more fertilizer talk. That must have been why that happened. I had fertilizer on the brain after having looked at this problem. That is the chemical structure of urea. Why make this make a good fertilizer? There's nitrogen in it. Yeah, that's great. Okay, so there's nitrogen in it. Fertilizers need to have nitrogen, they need to have potassium, and they need to have phosphorus. Those are the things that plants kind of end up having limiting. So those are the things that have in fertilizer. This is good. This is also your body's way of getting rid of excess nitrogen. Okay, so when you pee, There's urea in there, getting rid of excess nitrogen, especially if you're on one of these high protein diets. You're going to be excreting a fair amount of urea. Okay. But back to here. We're investigating the properties of fertilizer. 10 grams of urea, there's that, is dissolved in 150 milliliters of water, a simple calorimeter. The temperature change from 20 changes from here to here and is measured. Calculate the molar enthalpy of solution of the fertilizer urea. Okay, so we want to know the molar enthalpy of solution. So does it absorb heat or release heat? Well, first off, look at this. Does it absorb heat when it dissolves or release heat? Did the solution get colder or hotter? Colder. Got colder. It's like a chemical cold pack. And in fact, I think urea may be used in chemical cold packs. It's not very toxic. And so what we've got is that's going to absorb heat. All right? So if we think about this, if we were thinking about urea, let's go ahead and I'm going to do urea like this because I can write this faster than I can actually write. Nah, that'll be confusing. I'll write it like this. So they're kind of showing you the structure in this one because it wasn't out of your book. Instead of putting all the atoms together. So the structure is this. You see how they're kind of showing you the structure in the way they wrote it? This nitrogen has 2 hydrogens attached. This carbon has an oxygen attached. This nitrogen has 2 hydrogens attached. That happens sometimes. So this solid goes to urea aqueous, okay? And I haven't left myself a lot of room here, but where do I put heat in this equation? Exactly, heat is a reactant. It's endothermic, it gets colder. Heat is a reactant. It's absorbing heat, okay? All right, so now we need to do this problem. We have a simple calorimeter. So in other words, they're not telling us anything about it except that it has 150 milliliters of water. So consider it's like if you've done your lab already, it's a coffee cup calorimeter. It's just a piece of styrofoam that insulates pretty well. And so you've got the water. All we care about is the change in temperature for the water. So we're going to use this equation. Change in temperature. Calculate the molar enthalpy of solution. Okay, so it didn't tell me I had to use joules or calories, so I'm going to use calories because calories is easier. Okay, it's a 1, right? So my specific heat capacity for water is what? I just said it, 1, right? 1 calorie per gram degree Celsius. Sorry. Degree Celsius. Times, what's the mass of my water? Do you know what the mass of water is? What's the density of water? 1 gram per milliliter, right? So 150 milliliters of water is 150 grams. You okay with me not doing the conversion? Anybody want the conversion? Just nod. Okay. So 150 grams of water. Grams cancel with grams. And then my change in temperature is 20.4 divided by or minus 16.7. I'm not doing that in my head. Anybody better at doing math in their head? There's a 7. Is it 3.7? 3.7? Okay. 3.7 degrees Celsius. Okay. Celsius cancels with Celsius. I'm going to be left with calories. Right? That's great. All right. So 150 times 3.7. $555? Yes. Actually, 560? To get the significant figures right? Okay. So we have that much heat was produced. Now we need to figure out how many moles of urea there were, right? So if we're going to do this, so This is the heat produced. All right, and so then our question is, how many moles are in 10 grams of urea? So for that, what if I want to figure out moles of urea from grams of urea, what do I need? The molar mass, right. Anybody already calculated it? Yeah, Tyler. 60.05. Okay, so the molar mass of urea, I'm going to go CN2H. Oh, there's a 4O. Maybe I should have put the H first, actually. I'm going to rewrite this. I think the convention here is to go from left to right on the periodic table, except for the hydrogens. Okay, so the molar mass of that is, you said 60 point what? 60.05. 05. Okay, I'm just going to, yeah, I'll go 05. Grams per mole. I have 10.0 grams of urea. I'll just do a U here. If I have 60.05 grams of urea, I have 1 mole of urea, right? Grams of urea, cancel with grams of urea, and now I'll get moles of urea out of that. And that's going to give me 16.7, no, I'm sorry, 0.167 moles of urea. Do the people get that? Okay. All right, and so then let's go ahead and, so then I have my heat divided, I want calories per mole. I've got the calories produced by this many moles, so I'm just going to divide one by the other. I'm just going to do it right here. So 560 calories divided by 0.167 moles is going to give me the units I want, right? Calories per mole. And that's going to be 560 divided by 0.167. And I've got, oh my gosh, a big number. Okay, but that makes sense. 3350, because I've got, my 560 is only 2 significant figures. Once again, I'm going to do the significant figures correctly, but you shouldn't, you just need to be close. Okay, so calories per mole. I definitely don't want you spending most of your intellectual power on significant figures, right? I don't want you getting hung up on significant figures and missing the other more important stuff. Okay, so that's what I got. Is that what other people got? I see some sort of nods. Okay, great. So those are enthalpies of solution. And they're important. We've had multiple real life examples where people use this sort of thing. Questions before I move on? We're going to talk about enthalpies of reaction now, which are also super important. All right, so I'm going to call enthalpy of reaction is the amount of heat given off or absorbed in a given reaction. All right, so what we're going to do is we're going to treat heat as a reactant or a product. I'm going to say as a reactant or product, but as a chemical reactant or product. Okay, so that's going to give us some rules here. It's going to be part of our equation. It's going to be a number, right? So in other words, if we were to write our reaction up here, we'd have urea. So we could have urea solid going to urea dissolved, so aqueous, right? And we would have 3,400 calories as written right here. Okay, so 3,000 calories. That. Okay, and let's go ahead and put it per mole. And so if I could use this just as a conversion factor when we go to do reactions. We go and we use the ratios from our chemical equations. We could use 1 mole of urea gives me this much. Okay, 4 moles would give me 4 times that much. So I'm going to multiply by things. If I have to multiply my whole equation by 2 to make the oxygens be even numbers, I'd have to multiply my heat by 2. Okay, so you're really just going to treat it the same way we treat everything else in terms of when we're balancing and using these chemical equations. So we're just going to jump right in here and let's just do a problem. All right, and what I think I'd like you to do is, let's have you try this one on your own. I haven't done an example. All right, but if 18.19 grams of magnesium carbonate decomposes to form magnesium oxide and carbon dioxide, how much heat is released or absorbed? Is heat released or absorbed? Or endothermic, exothermic? It's positive. It is endothermic. It's absorbed because it's positive. Positive means energy is being added. This is our system, right? These atoms, energy is being added to them. So it's positive. If it was negative, energy would be subtracted from them and be released. Okay, so it's positive. If that doesn't work for you, if it's positive, just memorize that what this is I'm going to treat it like a reactant. 0.7 kilojoules. Okay, and they didn't write per mole, so I guess that's a convention. I'll follow that. I'll stay quiet for like a minute or two here, and then I'll give you a hint. But if you want to call me over before that, happy to help you get started. Okay, so if you were having trouble getting started here, this is, you know how we have our moles highway, right? You go to moles, so we can have a grams to moles problem, we can have a grams to grams problem, right? This is a grams to moles to heat problem. Okay, so grams to moles, we've done that a lot of times. We're going to use our molecular mass to get from grams to moles. But then if we want to go from moles, then we go from moles to heat. And we use the ratios from our equation. This one doesn't have any complex ratios in it. I should have maybe picked something else. But so 1 mole of magnesium carbonate, because there's a 1 in front of there, right? 1 mole makes 100.7 kilojoules. So that's your conversion factor. Go ahead, 2 more minutes, and then we'll work it together. Sorry about the construction noise. All right, let's go ahead and try this one. Or let's go ahead and work this one. You guys just did try it. So we start out with 18.19 grams of magnesium carbonate. We've done the molecular mass calculation a bunch of times. I'm just going to get it from one of you. Anybody have it? No, look at you, Tyler. 52.3, thank you. So 52.3 grams of magnesium, that's a magnesium carbonate, is equal to 1 mole of magnesium carbonate. Grams cancels with grams. All right, now we need to go to heat. And so we know that from our chemical equation that 1 mole of magnesium carbonate makes 100 kilojoules. So 1 mole of magnesium carbonate is going to make 100.7 kilojoules. And so moles cancels with moles, and now we're at the point where we multiply across the top and divide by the bottom. So in my calculator, I'm putting 18.19. I'm going to skip the ones times 100.7 divided by 52.3. Okay, and I've got 35. How many sig figs do we have here? We actually limited to 3 by that one. Some of you may have 4 because of that, but I've only got 3 with what I wrote down, so I'm going to go with that. 35.0 kilojoules. Well, not per mole, just kilojoules was released. Or no, absorbed, right? Yes.
For the molar mass, I got 84.
You got 84? I got 84 instead? Okay. So let's go ahead and put 84. 84 point what? 32. Oh, yeah, no worries. Thank you for being willing to give me one. So I'm going to go ahead and just fix the answer here. Actually, I should have just asked you guys for the answer. And if two or more of you got the same thing, it was probably right. How about 21.72 kilojoules? Does that work? Okay. Questions? All right, so that's enthalpy of reaction. It's not really different from what we've done before. We're just treating heat as a reactant or product, and then we're using our ratios from the equation to get that. We won't bother with any more of those. But one thing with my example, I wish I had some numbers in here, because if there was a 2 in front for the balanced equation, if there was a 2 here, I'd have to put a 2 there. Okay, right? All right. We are ready to work our way into Hess's Law, which is really exciting. Hess's Law is really cool. Okay. But it is a bit of a change in gears. And what I want to do before I talk about Hess's Law is I want to talk about something called state functions. Okay. State functions are things, they're characteristics that do not change depending on path. Which may seem a little bit weird. So, what's everybody's favorite beach in Virginia? Sorry, I can't hear you. Buckroe? B-U-C-K? Like Buc-ee's? All right. So, the difference between elevation at Buckroe Beach and Salem is, I was looking this up while you were working things. It's 100 or 1,175 feet. Okay? So that's the difference in elevation between where we are right now and what it is in Buckroe Beach. All right? This difference in the elevation does not change dependent on how you get from here to there. Okay, does that make sense? So the elevation change is a state function. Does that make sense? Doesn't matter. So I could drive straight from here to there, okay? And the difference in elevation will be 1,175 feet. I can drive to California, and then I can drive from there, drive to there, and the difference would still be 1,175 feet, right? If we do take the absolute value for it. I could fly in a plane, so I would go up, right? Now I'd go up way up above that level, and then I'd come back down. It would still be the same elevation change. Does that make sense? Okay. But the path I take to get from here to there is not a state function then. Okay, and so I could I'm not going to put it on my phone because it would take too long, but I could put into Google Maps that, and Maps would give me a couple different ways, right? What else at maps would give me would not be a state function between Buckrow and Salem? The distances would be different. What else would be different? The travel time, right. You get a bunch of paths, right? You're like, oh, which of these do I want? I mean, it picks one based on whatever selections you've made previously. But you could change your travel time if you wanted to go somewhat slightly different. If you want to stop at Chipotle on the way, perhaps. But something like that. So does that make sense what a state difference is between a state function and a not state function? All right, so we have state functions in chemistry as well. If we go up to, let's go up to this reaction right here. Let's see, this. Okay? The amount of heat produced when a mole of urea dissolves in water is a state function. It's always the same. Okay? The path might be different. I could heat my urea up, I could synthesize urea, I could break it down and synthesize it again, but when I could go from here to here in a different way. Let's say I could break this down into its component elements, I could resynthesize it, and then I could redissolve it. It's a little bit weird, but I could do it by any path, but that solution would be the same. Okay? I could turn it into a gas and then I could redissolve it. Okay, so what I want to say then is change in enthalpy is a state function. And the reason it's a state function is the start, it just matters what the start and end is, okay? So the enthalpy end minus the enthalpy start is going to be the change in enthalpy, right? We never really determine enthalpies. We worry about changes in enthalpy because that's something we can measure easily. If we want to figure out all the heat contained in something, that would be difficult, if that makes sense. All the heat energy contained in an object. Okay, that's a state function. And so what that means is that it doesn't matter how I get from one place to another, that's going to be the same. And so what this unlocks something really powerful. What it means is if I have some reaction now, let's say I'm going to go from A makes B, B makes C plus D, okay? And C plus D makes E, okay? What I can do, and let's say I have an enthalpy, I want to figure out the enthalpy change of A goes to E. Okay, well what I can do is if I have an enthalpy change here, and an enthalpy change here, and an enthalpy change here, I can just add those all up and I'll get that process. Because it doesn't matter how I get from A to E. Okay? So if I go to here and then I go to here and then I go to here and I add them all up, I get the enthalpy change from A to E. All right? Just like if when I was traveling from Buckrow Beach to Salem, if I went to Colorado, right? I'm at sea level, I go to Colorado and then I come back to Salem. Let me run these notes. So we have Buckrow Beach. We'll do that. Buckrow Beach. We have Salem. If we just think about elevation here, and I've got Colorado. Denver's high, right? Denver. Okay, and so just like if I travel from here and then to Salem, it's still the same distance, right? So I could measure, if I wanted to figure out how to get to Salem, what the elevation change is, I could measure this, I could take this elevation change and then this elevation change and add them together, and I would get that. That makes sense? I can add them all together. Okay, super powerful, because it means that if we have a set of reactions and it's really hard to measure something, we can measure it a different way. If there's an easier way to measure it. So let's go ahead. I've got some kind of abstract problems down here in terms of there are more of these A to E's, and then we'll do some real ones. But let's say we have the reaction here. So we have numbers associated with this, okay? And so the question is, what's the enthalpy for the process? Let me do this one. I'll do B, okay? B's a little more complicated. So what's the enthalpy for the process of A goes to C? All right, well, I know that if I take A goes to B, so I'm doing this one. I know if I take A goes to B, sorry, I'm having problems with arrows here, goes to B, okay, that's going to give me an enthalpy change of 20.0 kilojoules. And if I go B to C, that's going to give me an enthalpy change of 30 kilojoules. And what I can do is I can add these up, okay? And in chemistry, you probably haven't got a feel for this yet, but it's just algebra with chemicals, okay? It's not just algebra with chemicals in terms of your calculations, but the equations, it's just algebra, okay? I can do all the algebra things to it. If I do something to one side of the equation, I have to do it to the other side. Same thing. And so A plus B, I added up my reactants. A and B are my reactants. I'm going to add up my products. B plus C, add up my products. Now I'm going to add up my energies, my enthalpies, right? That should give me a change of 50.0 kilojoules, right? You guys with me so far? Now what do you see here? If this was an equal sign, like in an algebraic equation, what could I do? I've got B as a reactant and B as a product. I could subtract B from both sides and make it go away. Or if you're used to this equal sign, I can just cancel it, right? Because I have it on both sides of the equation. We did that for our spectator ions. Remember that? Okay, and what I'm left over with is A plus B. Not A plus B. A goes to C. A goes to C is all I'm left with here. And that's equal to 50.0 kilojoules. Does that make sense? Super cool. Okay, all sorts of things we can do with that. Go ahead and do that one. Actually, let's do this one first. Do A. Do A. Now, what reactions would you have to add up to get 2A and 2B? But go ahead and let's take a minute. Okay, I can't stand to be quiet any longer. All right, so we've got I want to make 2A to 2B, right? So I could just multiply everything times 2, all right? But I'm going to show you, so I could just say, okay, I'm going to multiply this by 2 and this by 2 and this by 2, and my answer would be 40 kilojoules, okay? That makes sense. That may be what you did. But the reason why it works is because I could take A to B and I could take A to B and I could add them together and I'd get 2A to 2B, right? And then I would also be adding up my enthalpy changes, which would be 20 kilojoules and 20 kilojoules to make 40 kilojoules. Does that make sense? Okay, now let's, do I have a real problem? I do. Let's go ahead and have you take 2 minutes and try to do C. And then we'll go on and we'll do one of these with real chemicals. And what you might need to do with the spoon is it tells us about something. You might need to flip reactions, right? Okay? And something I didn't talk about, I'm glad we came up with this, is when you flip a reaction, you have to flip the sign on the heat because you're going in the opposite direction, right? If a reaction is endothermic in this direction, it's going to be exothermic in that direction. If you're having trouble with the enthalpies, don't worry about that. Just think about how can I flip the reactions I have to make a series of reactions that I add up into a new reaction. Yeah, that looks good. Okay, I'm going to jump in. I've seen 2 people with right answers already, so let's do it real quick. So I need to flip these, right? So the important thing here is that if I have this process B to C and it has an enthalpy change that is plus 30, if I flip that reaction and go C to B, now my enthalpy change becomes negative. Okay, because if we think about B goes to C is positive, right? B goes to C is positive, so heat's over here. But if we go the reverse direction, C goes to B, now heat's over here. Heat's a product. Okay? All right, so we've got, I'm going to just I'll put a line through that to get it. Let's not look at that one. And then we're going to also flip B. I'm sorry, we did that. We're going to flip D to C, right? D goes to C, negative 40 kilojoules. Okay, and so then I'm going to add these 2 together. I'm going to end up with the reaction C plus D. Those are both of my reactants. I've got B plus C. Those are my products. And then I add up my enthalpies. Negative 70 kilojoules. And over here I have now C and C on each side of the equation. Now I have D. I've made D plus B, or D goes to B just like that by flipping these, adding them, and canceling things that are common on each side. Questions on the process there? Okay, super cool, super useful, because now I don't have to always measure. If I want to figure out, let's say this reaction down here, oh, we're not going to get to standard enthalpies of formation. That's okay, we'll do it Friday. That's super cool too. So if I've got this reaction here, how do I solve it using these reactions? Let's say I know what the enthalpies are for all these reactions. I don't know the enthalpy for this reaction. I can make this reaction using these reactions. We have 6 minutes left. Let's focus mostly on, well, I mean, it's very little to add the enthalpies in the end, but mostly think about how can I flip these things to get that, and remember, and you might have to multiply something times a number, a reaction times a number to make everything cancel nicely, okay? And if I do that, let's say I took this bottom one, and if I had to multiply this by 2, right, to make things cancel nicely, then I'm going to have to multiply this by 2 as well. That's 5. Okay? So if you flip them, you change the sign. If you multiply the whole reaction by something, you have to also multiply the heat by that number as well. So work on how are we going to flip this? How are we going to make this work? And what I would do is I would focus most on looking at things I need and flipping them, and then I worry about multiplying. I hate to talk over you, but I'm going to. This one, do I flip it or not? Don't flip it. I'm getting a don't flip it. What makes you say that? CH4 is on the correct side. It's on the left side, and there's not. So I don't want to flip it over to the other side. How about this one? Do I flip it or not? Yeah. I do flip it because it has CO, right? It's the only one with CO in it, and CO is on the other side. So I need to flip it so that CO is a product and not a reactant. That's the first process. How do I get products and reactants on the right side? And then, can I cancel everything? You're actually going to have to multiply something by something here. I'm going to give you one minute here. We're going to run out of time. I'm going to give you 30 seconds to try and get those all flipped, and then I'll write it, and then I'll let you continue. Okay, so we figured out for the bottom two, right? The bottom one, I'm going to rewrite it here. We don't flip because we want the methane, the CH4, to be on the left. Methane, by the way, is natural gas. It is the main thing that burns when you turn your stove on or you turn those burners on in lab. Okay, we don't flip that one. The other one we said we did flip, right? Because we needed carbon monoxide, CO, to be on the right side. It needs to be a product. So we're going to flip that one. So that's going to be 2 CO2 gas goes to 2 CO gas plus oxygen to make, and that enthalpy change is going to flip the sign, so it becomes positive 566.0 kilojoules. Okay? What about the top one? Is there anything in the top one that it's only in one of these? Run a short time here. So you see we have H2 here, we don't have H2 anyplace else, and H2 is a product, so I need to flip or not flip? Flip. So this is going to become 2H2O gas goes to 2H2 gas plus oxygen gas, right? And I flipped it, so I have to flip the sign. Positive 483.3.6 kilojoules. Okay, I've got 1 minute left here, so I'm going to go ahead and see if I can quickly do this. Can I add them directly down? What's going to cancel here? I do have 2 oxygens here, and I have 2 oxygens there. That's promising. I'm going to just go ahead and cancel them now. I can do that, right? What was that? Do I have a CO2? I have one CO2 and I have one up there. So I can cancel one of those CO2s. I'm going to make that a 1. I'm going to cancel that one. 2 waters and 2 waters. So what is this going to give me in the end? Is this going to give me what I wanted? Is it that easy? 1 CH4. I've got a CO2 left I have to get rid of. Okay, so what I'm going to need to do, since I need to get rid of the CO2s, I'm going to need to multiply this right here, this one right here by, or I'm sorry, this top one up here by 2, so I can cancel my CO2s. Okay? And if I do that, we're not going to do the whole problem here, but let me just show you what I would do for that part, and we will start with one of these on Friday. But I would multiply by 2, this would multiply by 2, I would multiply this by 2, I would multiply this by 2, and I guess this is the one I did for my example, 1605 kilojoules, okay? And then I would try canceling and see if I got the right thing. All right, you guys have a good couple days. I will see you on Friday. If you want to come see me for